welcome to this episode of Foundry Fireside. My name is Dasha May Hosley, and I'm an intern on the Foundry's communications team. Today, I'll be chatting with one of the Foundry's postdocs, Chengshuang Zhao. Chengshuang works with Dr. Jeff Urban, researching materials for renewable fuel generation. Thanks for joining us. Tell us a little bit about yourself.
Yeah, thanks for having me here, Deshame. My name is Chengshuang. I did my PhD in chemical engineering at Stanford University, and I joined the Foundry last year as a postdoc.
Thanks, Chengshuang. Can you tell me about your research and why it's important?
Yeah, of course. So, as you mentioned, I work on the development of heterogeneous catalysts for CO2 conversion. And on the side, I also work on the fundamental understanding of catalyst structure as well as their reaction mechanisms.
Can you explain the process of converting CO2 into methanol and/or methane in simpler terms?
Yeah, I'll try my best. So, generally speaking, we're talking about chemical reactions and processes where CO2 reacts with other reactants to produce desired products, such as methanol or methane in your question. And typically, we would need at least three components to make this happen, and they are reactant, an energy input, as well as a catalyst. So first, CO2 itself is a stable and inert chemical. So it needs another reactant that is reactive enough to actually turn it into something else. In most cases, or at least in most researches in academia, the other reactant is hydrogen, although the use of more abundant chemicals such as, say, natural gas is also studied. Now, second is the energy input. The rate at which this reaction happens at normal conditions is extremely low. So a certain amount of energy is required to drive the reaction at an appreciable rate. And third, which is what I think the most important, is the catalyst. Because on one hand, it accelerates the reaction, which would reduce energy demand. And on the other hand, the choice of catalyst can actually totally decide what product you get. Now, thermodynamically speaking, CO2 conversion, or we can use CO2 hydrogenation as an example, could in theory produce a wide range of chemicals such as CO, methane, methanol, ethanol, or even hydrocarbon fuels that are renewable, as you mentioned. So a good catalyst, which is what I'm trying to study and produce, should actually steer the reaction pathway towards the desired product with the highest selectivity possible.
What are some of the biggest obstacles in developing renewable fuels?
Yeah, that's really a good question. I think first of all, it really depends on our definition of renewability here. And I can only briefly talk about this aspect because it's not really my expertise. But one really important premise of CO2 conversion is to mitigate CO2 emission and to reduce carbon footprint, which should not be always taken for granted. For example, CO2 hydrogenation, which uses hydrogen as the reactant. The production of hydrogen actually notably releases CO2, which would compromise the renewability of anything that is produced from CO2 hydrogenation. So I would say the very important challenge here in this context should be extended to how do we produce the counter reactant, in this case, hydrogen renewably, for example, from electrolysis of water, maybe. And on the other hand, it also depends on what fuel we're talking about. Methane can be used as a fuel, and actually we know how to make it from CO2 conversion for a long time ago. There's this reaction called the Saptir reaction, where CO2 and hydrogen react to form methane, and it was discovered first in 1897, which is more than 100 years ago. But if we're talking about, say, gasoline range fuels, for example, hydrocarbons that are in the C4 to C12 range, then in academia, they weren't even reported until, say, 2010s. But if we take a bit further and say we're talking about even greener fuels such as ethanol, then actually there isn't still much progress yet, even in academia. So I would say, to put it in a more scientific way, we're still trying to understand how to engineer catalysts to selectively produce chemicals that have either higher economic value or higher energy densities, which would require not only fundamental understanding of the reaction mechanism, but also innovations in catalyst design.
What approaches do you propose to tackle these challenges that you mentioned?
Yeah, I think it really takes multidisciplinary collaborations, I think, because, in this project, we are part of a cross-institutional group with experts on catalyst synthesis, characterization, reactor engineering, as well as computational modeling. And at the Foundry, we are studying a new family of materials actually called high-entropy alloys And we're trying to develop characterization techniques to not only understand their structure, but also to understand their relationship with catalytic performances.
What are high entropy alloys?
Yeah, so alloys are mixtures of metals, and a binary alloy is the mixture of two metals, and they are actually widely applied in heterogeneous catalysis because a carefully designed combination of these two elements could actually achieve performances that actually surpass both constituents. And as I mentioned earlier, it really takes innovations in the design and fine-tuning of catalyst structure to improve the activity and selectivity of catalysts, especially in the context of CO₂ hydrogenation. And the types of metal combinations, or in a more scientific way, we call them the configuration of catalytic active centers, are actually quite limited when you only have two types of metals to play with. So hence high entropy alloy, which is an alloy made of at least 5 types of elements, which really offers us a greatly expanded compositional platform for us to engineer catalysts.
What makes you want or excited to research this topic?
Yeah, I would say what excites me most is that in this project, we're really trying to tackle a genuinely challenging scientific question. And at least so far, I haven't really come up with any straightforward solution yet. Um, you know, in heterogeneous classes, the conventional school of thought is to attribute a specific activity or selectivity, or in general, a catalytic performance to a specific catalyst structure or a structural motif. This has been both theoretically and experimentally verified by not only monometallic catalysts, but also binary alloy catalysts. And intuitively, you would want to extend this approach to high entropy alloys as well, because after all, we're just adding more elements into a binary alloy system. But even if we're just adding, say, 2 or 3 more elements into the system to make it a 5 or 6 element alloy, the total number of possible atomic configurations in the systems expands so quickly that it actually becomes almost impossible to actually count or pinpoint specific structures in this material. And I personally have done some projects on binary alloy systems during my PhD, but this new project really pushes me to think not only creatively, but also to explore new approaches. For example, since last fall, I've been learning the design of a characterization system or platform that would enable faster turnovers in iterative catalyst design, or high throughput catalyst screening, if you want to put it specifically. And I just finished building I believe Foundry's first prototypical reactor for catalyst testing. So yeah, it is really those opportunities in this project for me to not only apply the knowledge that I've learned and acquired during my PhD, but also to explore different approaches and to really solve different problems that excites me the most.
What is your hope for this research? If your research is successful, what could this mean for the future?
Yeah, I think the ultimate goal of this project would be to demonstrate an energy efficient, not only stable, but also selective CO₂ hydrogenation pathway to synthesize hydrocarbon fuels. So, one of the direct impact of this project would be to offer a promising alternative pathway for the mitigation of carbon emission and also the production of renewable fuels. But also at the same time, I think it's at least equally important to emphasize that we're also trying to offer more insights on the systematic understanding of complex systems such as high entropy alloys, whose principle could, theoretically be universal in the design and understanding of many other catalyst systems.
What makes you excited to do this work at the Foundry every day?
Yeah, besides everything that I just mentioned, scientifically, the challenge of this project itself, I think Foundry really has one of the greatest collection of staff members, and I really, really appreciate their support in every aspect of my project. And I think it's just great that, I have the opportunity to, go to Foundry and discuss and learn from experts in so many different fields.
That's all the questions I have today. Thank you so much for chatting with me. It was great to learn about your research. For those of you watching, if you'd like to learn more about the Foundry research, stay tuned for more episodes of Foundry Fireside.